Oh, okay. Finally, welcome to This and That, Monday, 10th of November. So, today we're taking a brief detour. It's not so much a detour as it is still relevant, quite. Uh, so, there's this article from 2004 on cultural topology and introduction to postmodern mathematics. And no, there won't be a lot of numbers, fortunately. So, now, this essay develops a new way of thinking about the cultural relationships among and within the sciences and the arts through a new understanding of the term postmodernism. Yes, I know people's eyes will glaze over, but that at once derives from literary theory and the mathematical discipline of topology. Now, let me break here for a second and say, yes, I know that sounds a little tedious and stupid and whatever, but this is the kind of stuff that Zizek is talking about, mainly because it overlaps with his kind of discussions of Lacan, among other things. So, but this is not about Zizek necessarily. Anyway, within the sciences and arts, through a new understanding of the term postmodernism that it once derives from literary theory and the mathematical discipline of topology. While topology forms the main vertebra of this connective approach in its capacity as the mathematics of connectivity, quantum mechanics and non-Euclidean geometry, the atlas and axis of this spinal column form the context through which this postmodern approach will develop. However, in order to position topology as a quote unquote postmodern branch of mathematics, some brief explanations are in order. First, regarding postmodernism, and finally, regarding topology. Postmodern and mathematics are two terms that are not usually grouped together, not unlike deconstruction of mathematics, especially among mathematicians. Mathematics is a well-defined pursuit, complete with its own homed, exhaustive sets of protocols and a body of willing participants eager to disseminate the contents to all those who wish to receive it. Postmodernism, on the other hand, is more ephemeral. Though a growing group of scholars in the humanities and social sciences have been referring to them as postmodernists since the 1980s, by and large, postmodernism does not yet carry the same weight as mathematics. Outside of passing hallway conversations or classroom exercises, postmodernism has no identifiable home. There's no department of postmodernism, in other words, no clear definition, and certainly no consensual set of protocols. Generally speaking, postmodernism and mathematics are two very different kinds of things. One cannot point to the pages of a book or a carton of milk and exclaim, "There, you see that? That's postmodernism." Well, yes, you could actually. Like it was just mismarked and placed on the wrong aisle. However, over the last decade, there have been many attempts to place the larger areas that claim ownership of these disciplines, namely the arts and sciences, into a dialogue with each other. The volatile union of these two sets has produced what is now called the quote unquote science wars. The feeling is that if the parent companies begin negotiations, maybe their prodigal subsidiaries would be less apt to quarrel and fight over property rights and copyright infringements. The point being, of course, is actually that's where the real issues lie. Many of the recent debates have centered on the ways in which the arts have used and or misused the sciences in their many or their highly public arguments. The criticism, mostly from scientists themselves, is that many in the emerging area of science and technology studies, that is STS, not a disease, or cultural studies of science, CSS, no, it's nothing to do with your webpage, base their critique on uninformed assumptions about what science is or how it is done. Let me break here for a second. And, the whole question of human sciences is always at issue. Anyway, in 1996, theoretical physicist Alan Sokal, like Hephaestus, 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 rigged his own net, hoping to catch an unsuspecting adulteress. This fraudulent article taught a lesson that will not be soon forgotten. My essay, while perhaps a partial or provisional response to this kind of criticism, let me break here and say parenthetically, yes, that hasn't stopped. There's a trio of clowns, mainly from Portland, of all places, that has tried to do this yet again, as though doing it the first time wasn't sufficient lesson enough to the humanities. But anyway, my essay, while perhaps a partial or provisional response to this kind of criticism, seeks to reconfigure the long boiling issue between the arts and sciences over the term postmodernism in a different way. In brief, then, let me summarize the form of this issue. Many scholars in the growing area of STS and CSS in general tend to frame science as a product of culture, like the media or religion. That is, they have tended to view science as part of part of culture rather than apart from it. And as such, so the argument goes, science can be analyzed as a cultural institution, just like it's a social institution. The history of science is rife with those who have conducted their experiments under this assumption. Unfortunately, only a select few in either science or cultural studies have developed a means by which these two traditionally separate areas can be combined in such a way as to either avoid simplifying the inherent complexity in both, or in such a way as to not make one an instrumental product of the other. And the war, as I see it, has generally taken one of these two forms, one of which tacitly support the age-old dichotomy and one of its more vitriolic manifestations. For example, science rightly concedes Steve Fuller's characterization of post-war programs like Harvard's General Education in Science as a, quote, remedy to normalize the role of science in society so that it not seem irretrievably alien, close quote. And while he is careful to emphasize that such programs were intended to train future managers of scientists who themselves had little scientific training, his work borders on hypocrisy in light of Norman Levitt's criticism of this misunderstanding of set theory. Fuller's hearkening to C.P. Snow's famous imperative, yes, the two worlds, whatever, two cultures, that the science curriculum should adapt to include courses that promote an understanding of the cultural and social context in which it finds itself, is matched by Levitt's argument that the liberal arts should do the same. Indeed, This is a core curriculum argument. In mathematics, as the stepchild of contemporary culture, Levitt suggests that today the liberal arts is something of a misnomer, as the more rigorous subjects of the traditional liberal arts education, like math and mathematics, have all been abandoned since the 19th century. Yes. So, within the generalized miscommunication of the maelstrom of cries from both sides, lie two kinds of thought that have not always been so distinct, according to Levitt, certainly not to Aristotle. Fortunately, for those who feel a stronger connection between science and culture than one of incidents or accidents, with a CE, one of wholesale misappropriations or even a misunderstanding, there's been a steady growth in approaches over the last decade that seek a kind of connection, new kind of connection, a connection I will call postmodern connection, even in spite of the almost unholy connotations this term now carries in academic debate. The work of Floyd Merrill in Semiotics, excellent major text by Floyd. Arkady Plotnitsky in literary theory, Andrew Pickering in sociology, comparative scholar Brian Rodman, and poet Jonathan Holden stand out in this regard. And it must be readily conceded that my use of the term postmodernism, while deriving from the sociolinguistic post-structural theories of the late 1960s, yes, it did exist, is not reducible to them. This essay develops a new way of thinking about the cultural relationships among and within the sciences and the arts through a new understanding of the term postmodernism that at once derives from literary theory and the mathematical discipline of topology. Now, while topology forms the main vertebra of this connective approach in its capacity as the mathematics of connectivity, quantum mechanics, and non-Euclidean geometry, the atlas and axis of this final column form the context through which this modern approach will develop. However, in order to position topology as a quote-unquote postmodern branch of mathematics, some brief explanations are in order. First, regarding postmodernism, and finally regarding topology. Let me break here for a second, and I think you sort of can see how the introduction goes and the reason for doing it. And note, of course, that this does not stop there. You know, Badiou's interest in category theory, set theory, etc. Yes, there is the semiotics of math. You know, there's actually activity in this area. People don't make this stuff up. There's actually scholarly activity in this region, sub-region of the curriculum. Anyway, number one, introduction, back to the text, avoiding a definition of postmodernism. And for the last 40 years, yes, 40 years, hardly a year has gone by in which the humanities, the social sciences, in which the question, what is postmodernism, has not been raised on one formal level or another. And the single greatest deterrent to overcoming the quarrel between the sciences and the humanities is the inherent resistance of this term to definition. Year after year, science asked for a clear and precise definition of postmodernism, and neither the social sciences nor the humanities can offer one, since any and all definitions of postmodernism lead to, yes, tautologies. To use the language of science, these contradictions arise because the nature of postmodernism varies relying on who is conducting the experiment and in which lab the experiment is performed. The kind of postmodernism titrated in sociology laboratories is intrinsically different from the kind brewed in creative design laboratories. So, more like a quantum phenomena, which will be explained in due course. The kinds of experimental determinations that are used to observe postmodernism actually determine the nature of it. The kinds of experimental determinations that are used to observe postmodernism actually determine the nature of it. Now you can see there's a whole bunch of problems there. Therefore, since definition is no longer defined within the axiomatics of postmodernism, we must ask different kinds of questions. First, we must determine the nature of the attempt, since this determines whether or not the term is to be celebrated, as in the social sciences, or mourned, as in the humanities. And second, we must determine for whom it is defined, be those scholars in a highly specialized field, French neo-fascist youth covering their faces with keffiyeh, oh, well, anyway, at a pro-Le Pen rally, or fans of the Simpsons television show. Admittedly, mathematics is more equipped to deal with an entity like postmodernism, since mathematical entities need not be defined in order to be utilized. Even the most cutting-edge research in intuitionism, the dominant philosophy of contemporary mathematics, has yet to provide a sufficient definition of quote-unquote number, which gets us into a whole bunch of other interesting issues. By and large, mathematicians are as content as Platonists. The sinuous axiomatics of postmodernism contains many contending propositions. However, it is significant that no postulate can be found. So rather than define the concept of postmodernism, a development of some central propositions would better suit the endeavors of this essay. For the purposes of this essay, the term postmodernism will come to designate a certain set of propositions that I will develop alongside an account of its conceptual history according to the humanities and social sciences. You see, already there's a problem. In avoiding definition, which would imply a sense of conceptual completeness or totality, postmodernism derives from certain propositions, such as mathematics teaches us, are always open to debate. These propositions derive directly from accepted conventions and assertions from within cultural studies in general and literary studies in particular. The only assumption on my part is an audience with a vested interest in cultural intersections among the sciences and humanities. Yes, I never really left that discourse area. And it is the nature of this intersection that I understand to be postmodern in the general sense that neither the sciences nor the humanities are thought of in absolute or complete ways. This amounts to identifying C.P. Snow's famous two cultures thesis as no longer applicable to the current state of affairs in either number two, in either, period. Sorry. This amounts to identifying C.P. Snow's famous two cultures thesis, a very good but very small or short book, as no longer applicable to the current state of affairs in either. Number two, section 2, the postmodern theorem. Yes, theorem. My understanding of postmodern derives directly from the genealogy we in the humanities have constructed. One usually traced through a group of French academics from the late 1960s who worked together to forge the theoretical groundwork from which the term comes. However, the form of my narrative follows mathematical practice, postmodern purism, the conceptual history of postmodernism, modern purism. The conceptual history of postmodernism, is a collective rather than individual development. Suffice to say that as a general rule, in the humanities and many of the social sciences, the birth of postmodernism, well, perhaps the birth of postmodernism dates to the moment Jacques Derrida presented his paper Structure, Sign, and Play in the Discourse of the Human Sciences at the Johns Hopkins Conference on the Language of Criticism and the Sciences of Man in 1966. However, as New Testament narrators like Matthew and Luke have taught us, the account of the Nativity varies depending on the narrator. While remaining a product of the mid to late 1960s, the actual date of the birth tends to vary as early and specific as July 25th in Newport, Rhode Island at 8:45 p.m. and as late and vague as the Watergate scandal between 1972 and 1974. Let me break here for a second. Yes, in fact, these all can be done. Much like you want to put it at 1968 or or the original literary theory of it, which goes back to something like 1930 or 1940, actually, is the first instance of its invocation within the context of the humanities. Anyway, Proposition 1, postmodernism is performative. Corollary, postmodernism has an epistemological rather than, even there is a problem, rather than an ontological status. Though the humanities and social sciences have used the term for 30 years, for the hard sciences, physics, chemistry, and many include mathematics in this list. The term postmodernism is a bit of a misnomer insofar as their practitioners do not tend to use it when describing their work. Likewise, it is also telling that when these hard sciences had their respective postmodern revolutions in the earlier part of the 20th century, the linguistic turn, the mathematical turn, etc., they each thought of the revolution in similar terms as a radical paradigm shift. And hence we get back to the original or the more authentic version of the question of paradigm shift. Proposition 2, postmodernism designates a radical conceptual shift in the established structures of interpretation of a given system of thought. For example, mathematics began its postmodern revolution at the turn of the 20th century with the development of mathematical philosophy, which culminated in 1931, which Kurt Gödel's on formally undecidable propositions brought the three contending mathematical philosophies at the time to their knees: logicism, intuitionism, and formalism. Gödel's humbling discovery that within any given area of mathematics, he chose the still young field of logic. There will always be certain propositions that cannot be proven true or false using the rules of that branch of mathematics alone. It caused a major revolution in every branch of mathematics, the most profound of which was in logic itself, and yet they still teach it. Unequivocally accepted by all branches of mathematics, Gödel's proof forced mathematics to come to terms with its own foundations, its own raison d'etre. Proposition 3, as a method of analysis, postmodernism interrogates the fundamental assumptions upon which extant structures of thought are predicated. The proof of the absolute undecidability of the consistency of mathematical reasoning, rather than pronouncing a death sentence, actually resuscitated the quickly expiring body of mathematical philosophy. When Jacques Derrida presented the same hypothesis in form rather than in content to the humanities in 1966, the result was more strangulating than resuscitating. Proposition 4, postmodern methods of analysis demonstrate the ultimate undecidability of a given system's truth values. In answering one of mathematics' oldest questions, Gödel's proof caused a revolution in the way mathematicians thought about their subject. In the text Infinity and the Mind, 1982, Rudy Rucker characterizes the nature of Gödel's answer as political and liberatory when he claims to understand the essentially labyrinthine nature of the castle, that is mathematics, that mathematics is, somehow to be free of it. And unfortunately, let me break here for a second, in one's mind, it is the, Monty Python storming of the castle, the French castle, as it were, with a cow flying through the air that comes to mind. Proposition 5. The aims of postmodernism are political. Proposition 5. Since Descartes, a significant portion of Western thought has been occupied with the struggle between the scratch and sniff British brand of empiricism And I believe it in spite of not seeing it. Oh my God. Occidental brand of rationalism. Gödel's answer to this dilemma, Rucker speculates, is that rational thought can never penetrate to the final ultimate truth. Gee, darn Hegel. Uh, Mathematics was one of the earliest disciplines to face its own mortality and survive to tell the tale. A decade before, a new breed of physicists placed the mirror up to the classical Newtonian physics and found similar results. Among them, that their methods of utilizing measuring devices like mirrors needed a radical reconceptualization. A decade later, fascism would force political scientists to reconceptualize how they defined even the most basic of political categories like right wing and left wing, nationalism and sovereignty. Proposition 6. The political dimension of postmodernism aims at internal change rather than external. Corollary. The political agenda of postmodernism aims towards its practitioners rather than its consumers. Darn navel gazing. The humanities, unfortunately, were fashionably late to this dance with the absolute. And to be sure, this is precisely how particular disciplines such as literary studies, oh, heaven forfend, conceptualize their own axiomatics as an absolute beyond which there was only opacity and nothingness. Arriving 30 years late to the dance had its price as literary studies started down a path of neurosis over the devaluation of their medium, that is, language, occasionally creating compulsive rituals to ease the obsessive anxiety of the loss. After a pirouette, mathematics and physics resumed their work and developed new areas of inquiry in spite of their own disciplinary devaluation as nuclear physics and, yes, category theory. Of these postmodern areas to explode after Gödel's proof, topology eagerly embraced this inconsistent logic. In fact, this inconsistent internal logic is the very fuel of topological analysis. For example, Douglas Hofstadter reminds us of Gödel's second theorem, which asserts that only propositions asserting their own consistency are themselves inconsistent. And as a kind of response to Gödel, algebraic topology, for example, transforms the logical concept of consistency into the spatial concept of connectivity. And since consistency is not provable within any given axiomatic topology, is able to transform the nature of the problem from one of logic to one of space. And yes, that encapsulates an entire decade of activity, starting perhaps with Lefebvre. But anyway, as I shall now show, mathematical space contains an infinite number of axiomatics, which Felix Hausdorff conveniently first calls neighborhoods in 1914, a kind of patchwork space. Topological analysis can combine them within a single topological field. Yes. Oh my God. Though Gödel's theorem does not coincide with the initial body of work of the early topological analysis found in Bernhard Riemann, Henri Poincaré, Hausdorff, or L.E.J. Brouwer, such early work seems to utilize a certain understanding of his ideas. In the next section, a selective history developed to help illustrate these connections. The first example is the most well-known and most understood of topological oddities. Yes, the Mobius band or strip. Number 3, a brief history of topology. Part 1, the patchwork of topology. As a discipline of mathematics, topology has existed for only 70 years. Though antecedents go back centuries, the history of topology, like so many areas of mathematics, more closely represents a patchwork quilt than a neatly bound tapestry. Leonhard Euler discovered the first topological property in 1750. And 1750, in fact, could be a postmodern moment. But anyway, the second was not discovered for another century. So 1850, 1750, interesting years, right? The first real work in topology did not appear until the turn of the 20th century, when Brouwer, considered the father of modern topology, unified some of Poincaré's work on differential equations and published the first fixed point theorem in 1909. Little comfort to the non-mathematician, topologists themselves have a hard time defining what it is they do, though it started as a kind of geometry and colloquially referred to as a red rubber sheet geometry, not unlike, if you, with all due respect to a rubber sheet geography. Today, topologists are an eclectic lot spanning the gamut of mathematical pursuit, from analysis, that is calculus, to algebra and geometry. In Experiments in Topology, Stephen Barr seemed to have his hand on the pulse of the early process of disciplinization when he claims that topology is yet curiously hard to define. Number one, recognizing an overt process at work. He recognizes an inherent postmodern tendency when he claims that topology is its own goal, although, of course, he does not use this term. Number two, it is perhaps not surprising, then, that the story of topology, yes, it reads more like literature than history, more like Lewis Carroll's Through the Looking Glass of 1872 than Edward Gibbon's The Decline and Fall of the Roman Empire, 1776 to 1788. It occurs in fits and spurts rather than along a linear progression of discrete bundles. And while it is a relatively simple task to characterize topology as the study of continuity to non-mathematicians, or as the formal study of the features of geometrical figures that remain invariant under spatial transformations to mathematicians, neither fully captures the quote-unquote sense of topology. My quote-unquote selective history of topology tries to characterize the sense by describing some of its detail, by focusing on some of the detail of Mobius's discovery of the second topological property in 1865. A disciplinary narrative develops, one that reveals the latent postmodern tendencies in certain kinds of mathematical thinking. The latent postmodern tendencies in certain kinds of mathematical thinking. We could even blame Sokal as doing that. Anyway, to be sure, standard classifications such as the distinction between topology and geometry are necessary, not only to provide a familiar correlative for the non-mathematician, but more importantly, to provide a context, as topology can also be described as the mathematics of context. The mathematics of context. As postmodern cultural theory has shown, context determines the conditions under which meaning is produced. And we have many examples of this, none the least of which is the deployment, however misguided and misshapen, grok in Twitter, for example. But the proofs of postmodern science, such as quantum mechanics, demonstrate that a rigorous analysis of context reveals that not only are the most basic of concepts, such as protons and electrons, without any meaning, they lack any real existence. B, part two, Mobius and his band. Mobius and his band. Anyway, 1865, August Mobius, an admittedly mediocre German mathematician, began work on a strange, one-sided, two-dimensional figure that now bears his name, although Johann Listing actually published his finding on the Mobius band 4 years earlier, but doesn't quite sound as onomatopoetic. A Listing band would suggest that it's sinking. Anyway, what he discovered is that he tried to align triangles along the surface of the band, aligned triangles along the surface of the band. You can see mathematically how interesting that is. The orientation of the triangles had changed. Darn, those polygons had changed by the time he finished covering the surface. He described this property of one-sidedness as non-orientability. What this means is that when an orientable figure, that is one with bilateral symmetry like our bodies, for instance, traverses the length of the one-dimensional figure, the right and left sides of it become inverted as if viewed in a mirror, sort of the flatland problem writ large. For example, if a person wears an eye patch on his or her right eye, then whether they live in Finland or New Zealand, face east or west, or stand on their head, their right eye is always the one covered. Now, this is a simple demonstration of the orientability of the shape of the Earth, an ellipsoid, which raises interesting a question about antipodes, but anyway, that's another story. The only exception to this is the reflection of the one-eyed person in a mirror in which the eye patch seems reversed. The Mobius band is a perpetual mirror world in which it is impossible to tell which image is real and which is a reflection. If our friend with the eye patch over his or her right eye traveled along a Mobius band, eventually the patch would switch to the left eye. Now, at this point, a ready objection comes from cultural theorists who argue that the perspective can determine one's reality, even on an ellipsoid like the Earth. Up is relative, especially to the New Zealanders, antipodes, right? But orientability is different from mathematical perspective in that orientability is invariant in spite of perspective. Orientability is invariant in spite of perspective. Orientation is an internal property of a figure, while perspective is an exterior orientation applied to it. Gyroscopic in that sense. As a kind of internal perspective, the orientation only changes when the internal nature of the figure is changed, while exterior perspective changes as the external circumstances change and in spite of internal orientation. From the anterior, that is a pyramid, not only appears to be a square, that is if it fell over, but even the dimension appears different, 2 rather than 3. As the position of the observer changes, so does the perspective. However, the internal orientation of the period does not change. A Mobius band is an example of a figure or a space without orientability. A circle seems non-orientable as well, but with no inherent top or bottom, only a relatively defined one. But when half of the diameter is colored red and the other half blue, the orientation of a circle becomes obvious and remains even in spite of any color coding. However, a Mobius band is not orientable since there is only one side. Coloring only the top half of the band, which is relative in terms of perspective, becomes impossible, as eventually the entire figure will be colored red as well. The top of a Mobius band is the same as the bottom, just as the inside is also the outside. Just as the inside is also the outside. Without orientation, perspective itself is still possible because the fundamental distinction between self and other, between here and there, remains. From a distance, the Mobius band appears to be a figure 8. From a distance, the Mobius band appears to be a figure 8. darn those numericons. But without orientability, there is no inside or outside as one eventually becomes the other. Two-dimensionality, such as a piece of paper with infinite thinness, and three-dimensionality as kinds of spaces have a consistent orientability. And here it is helpful to think of space as an open, unbound geometrical figure rather than the last frontier, right? Mobius happened onto a intrinsically different kind of space than the usual three-dimensional version that we seem to inhabit. As such, he discovered the second topological property. For the same kinds of space, orientability is invariant. Topological properties like orientability are thus the most fundamental characteristics of figures in spaces, as they are invariant across drastic, albeit allowable, kinds of spatial transformations. And so, there's a material limit, as it were, right? In a sense, these properties form the core nature of all topologically similar figures, whereas geometrical properties vary even among similar figures. For example, a triangle and a circle are the same kind of topological figure because their topological properties are the same, even though their geometrical qualities are drastically different. You are a donut, for example. By following the rules of topological transformation, a triangle can be rounded into a circle, not unlike pro wrestling, which does not change its intrinsic qualities. Only the extrinsic quantities, distances, angles, degrees, volumes, dimensions, etc., change during topological transformation. And this little sentence here, you can see the attraction to it from a Marxian or Hegelian or Kantian point of view. In other words, this idea of discovering the intrinsic from the, point of view of, from a subjective point of view or whatever, as the subject point of view, as one might consider, you can see why Zizek would be interested in this, and not simply because of that, but also because of Lacan's discussion of a topology. But anyway, C, part 3, topology versus geometry. Topology is like geometry. It is concerned with the shape of space and how we understand or visualize figures within different kinds of spaces. However, whereas geometry is concerned with quantitative properties of geometrical structures such as lengths, degrees, and areas, topology is concerned with their qualitative properties. Now, even that is a problematic proposition, the qualitative as opposed to the quantitative as a comparing geometry to topology. So that interesting question there. But despite this difference, both disciplines share a concern for the kinds of transformations that are allowed. So you can see, Marx wasn't thinking visually in that sense, but conceptually, he was. Euclidean geometry, the familiar planar world high school students explore with, varying degrees of success, is the most restrictive of geometries. Two objects are considered equal in Euclidean space if they can be exactly mapped one on top of the other. Every point on one figure corresponds with every point on the other. Now, even though two triangles may have these same interior angles, that is, they are similar, if the lengths of their sides are different, then they are not congruent triangles. In this sense, topology is a much less restrictive kind of geometry. For example, the concept of distance is crucial for topology, but actual distance, that is, numerical values, are irrelevant. Hence, certain problems that we could say exist in a, as it were, quantitative geography. More than turning and flipping, topology, damn it, speaking more than turning and flipping, topology allows for all continuous transformations, such as bending and stretching, but discontinuous transformations such as cutting and puncturing are not allowed. Hence Derrida's interest in, cutting and puncturing and, the residuals of trace, et cetera, et cetera. A two-dimensional disk and a three-dimensional pyramid are topologically the same kinds of figures, since continuous transformations can change one into the other. Hence the black disc that gets thrown around in Warner Brothers cartoons that create tunnels or, voids or whatever. Anyway, conceptually, topology is the study of continuity. Rather than measuring angles and distances, topology looks for holes and sutures. The sutures notion is really important, as you could imagine, not simply as the suggestion of its physiology, as it were, but also the larger question of what it means in terms of a kind of seeking the absolute, as it were. Rather than measuring angles and distances, topology looks for holes and sutures. Ironically, when Euclidean geometry focuses on minute and precise ratios, see Marx, it is most efficient when dealing with the most simple of figures. And this may be, in fact, why Marx doesn't do figures. But anyway, geometric figures. In order for Euclidean geometry to determine the surface area of a complex figure, such as a coffee mug, it must first break down the complexity into simple elements, essentially a cylinder and a torus, right? Tubular bells. Ha! The donut shape of the handle. On the other hand, topology is able to analyze very complex structures in their totality without dissociation. In fact, as we shall see, topology is in a position to make qualitative statements about figures only because objects are understood in their complex totality. While both geometry and topology study figures and objects, real, impossible, or imaginary, real, impossible, or imaginary, I would assert much like competition. But anyway, each has its own set of rules and operations that are allowed. Each has its own set of rules and operations that are allowed. And it is this axiomatic that distinguishes geometry from topology. Now, as I suggested, the fundamental relationship in geometry is congruence through an exact mapping of points. Mapping of points, as we might think of them as one as opposed to two-dimensional, or the difference between one and two-dimensionality in that sense. To be sure, geometry has developed many theorems that allow one to avoid such an exact mapping, but the mapping itself is essential. So if this map cannot be produced through deduction or induction, theorems or postulates, then there is no congruence, only difference. See, we're already into Derrida, right? Then there is no congruence, only difference. In this way, geometry is concerned only with manipulating the extrinsic properties of a figure, that is, with its variable properties. Topology, on the other hand, is interested only in the intrinsic or permanent properties of figures. The concept of difference, while crucial in topology, is only important insofar as it remains consistent as a concept. Consistent as a concept. The concept of distance, consistent as a concept. For geometry, only the value of different distance is important. The nature of that value is irrelevant. For geometry, only the value of distance is important. The nature of that value is irrelevant. For example, geometry is not concerned with the nature of roundness, only the value or kind of that roundness. That is elliptical, hyperbolic, circular, etc. In topology, extrinsic determinations of distance or degree do not fundamentally change the nature of a topological object or its reliance on a consistent definition of distance. In topology, extrinsic determinations of distance or degree do not fundamentally change the nature of a topological object or its reliance on a consistent definition of distance. So that statement alone, that proposition alone, is an interesting one. As a kind of rigorous qualitative geometry, early pioneers in the field of topology began distinguishing among types of spaces, again, open and unbound figures rather than among different perceptions of those spaces, such as those in projective geometry. Hence the difference or the distance between, the modern and the postmodern. As we might assume, even if you're thinking of the Renaissance, the difference or the reaction to, Renaissance geometry with, let us say, post-Renaissance geometry or perspective that we might think about, even though it probably doesn't really go there with Vasari, for example. Many early topologists were trained as geometers, right? Many early topologists were trained as geometers, and much of their work evolved out of a dissatisfaction with the kind of space Euclid envisioned. So you can see, where the non-Euclidean can go, et cetera, et cetera. As my first example demonstrated, Mobius discovered that the shape of space determines what kind of orientation is possible. The shape of space determines what kind of orientation is possible. Now, this question of let me break here for a second and say, well, now, that's an interesting idea that there are a system of determinations then, perhaps, yes? In the 1850s, Riemann discovered that, well, our reality seemed to be Euclidean. It was not. Riemann was among a growing number of mathematicians who became dissatisfied with some of Euclid's assumptions about the nature of space, particularly his parallel postulate. Keeping the rest of Euclid's system intact, figures like Bolyai, Lobachevsky, and Riemann were able to create consistent geometries free of contradictions in which the parallel postulate did not hold. Early non-Euclidean geometries thus discovered that the shape of space determines the kind of geometry that is possible within it. Early non-Euclidean geometries thus discovered that the shape of space determines the kind of geometry that is possible within it. In thinking about the order backwards, that is, space determining the kinds of figures that are possible within it, non-Euclidean geometers were able to challenge the way mathematics thought about its objects of study as well. Unlike geometry, which can only compare quantitative differences since sameness is so narrowly defined, topology actually compares the qualitative similarities between objects. Hence, why structuralists would be interested in this, right? Why structural theories would be interested in this. Anyway, back to the text. In geometry, complexity is only understood as an instrument and extension of simplicity. Geometry distinguishes between circular and elliptical to arrive at quantitative statements about their differences, which can be expressed analytically, right? All those years suffering in high school. Topology understands complexity in itself in order to develop a detailed and formal method for dealing with the qualitative similarities among objects. In this way, topology is the basis for geometry. Since the nature of roundness, in this way, topology is the basis for geometry, since the nature of roundness in a formal and rigorous way, all those numbers and calculus, etc., forms the basis for concepts such as circular and elliptical. As a kind of postmodern geometry, topology analyzes the nature of the ground upon which its own self-construction lies. Even when dealing with the same object, geometry and topology approach that object in a radically different way. A common illustration to distinguish the two pursuits is the example of the London Underground. Geometry can be used to determine the distance from Piccadilly Square to King's Cross, while topology is more interested in how many different trains the trip will take. If you spend time in London for any degree of time doing the same route every time, you will get into this, sort of, as it were, interesting set of ideas, not necessarily about bridges per se, but you can see where this can go, right? While topology is interested in how many different trains the trip will take. So I will end here because I ran out of time again. We'll take this up again with tomorrow with part 4, D, topology as a pirouette. So we'll look at this tomorrow. And yes, this may all seem opaque to one, but once you begin to understand, how does Einstein get where he does? Well, he gets there because, the difference is this thinking in a Euclidean geometry as opposed, or in reference to, contextually speaking, to a non-Euclidean geometry, which is, key to getting, certain ideas about relativity going. But anyway, all that very important, and hopefully the math will become important as well. So let me go back to the meeting. Shut off the proverbial live stream, and remind you that we've been looking at an article on topology, cultural topology, by Brett Blackwell, an introduction to postmodern mathematics, in the journal. Yes, there are journals. Postmodern Science, fall of 2004, article 2. So anyway, there's that. And I'll see you anon, as they say.